This is a right triangle. Say we know all of its sides, but we don't know this angle. If you've taken trigonometry before, you know that you can find trig functions of that angle, like sine, cosine, and tangent. Now, say we only know one of the sides, and it's, 2 units long. But we don't know any of the other sides. Again, we want to know things like sine, cosine, and tangent of that angle. Since we don't know the other leg, we could give it a variable, x, let's say. We also don't know the hypotenuse, but Pythagoras has our back. Alright, so the sine, cosine, and tangent values of that angle look like this. Those are pretty fractions and all, but what is it good for? Well, this relationship actually gives us another way of rewriting integrals. For instance, if we happen to run into this integral, we can tell that this part of it is just cosine of theta. However, this isn't usually the way this goes down. Usually, we're given the integral first, and we come up with the triangle stuff later. Let's do that. First, though, I would like to establish what kind of integrals should make you say, I should use trig substitution. Having trouble evaluating integrals? Certain kinds of integrals giving you no way forward? If your integral has a sum or difference between a multiple of x squared and some constant, then trig sub might be for you. With trig substitution and a little bit of help from the Pythagorean identities, your expression turns into a single trig function.
Do not use trig substitution if you can integrate normally. Trig substitution may cause dissatisfaction with your memory of trig identities. Caution is advised.
Ask your instructor if trig substitution is right for you. To show the general strategy, let's try to evaluate this integral. You may notice that inside this numerator, or more specifically inside the square root, it looks kind of like something trigonometric. It's sort of like the solution for tangent squared in one of the Pythagorean identities. Listen, I know it's a stretch, but they're both something to do with a variable squared minus a constant. Bear with me. In fact, if we factor out a 4, we can make them even closer. The -1 matches now. So, I have a goal in mind. I want to change this so that the expression is the same. I want that first term to be secant squared. And I'm going to take a bold approach to get there. Since we want 25 over 4 x squared to turn into secant squared, I'm literally just going to set them equal to each other. Doing this kind of seems like it's against the rules, but it actually does help me set up what I need to substitute for x to make this work. Just like with u substitution, we're going to need to take the derivative and solve for dx. However, the solving part is easier here. Once we have substitutions for both x and dx, we can substitute. Things should work out more or less smoothly, even though there's a good deal of algebra. Sometimes you will have to use some more trig identities to rewrite your integral. Now, once you've evaluated your integral in terms of theta, we need to turn it back into x. But there's a problem. When we made up theta earlier, we defined x in terms of theta. That means we don't have an easy way to define theta in terms of x. We could try solving for theta by using an inverse trig function. But we can do better than that most of the time. So, how else are we going to find these two parts here? Instead, remember that trig functions like this tangent here are all just ratios of the sides of a triangle. So, if we can find the opposite and adjacent of a right triangle involving this theta here, then we can find tangent. And since cosine theta equals 2 over 5x, adjacent over hypotenuse equals 2 over 5x. So we can just let the adjacent of our triangle be 2 and the hypotenuse be 5x. Pythagoras saves us again by helping us get the opposite side. Looks familiar. Since we have both the opposite and the adjacent now, we can divide them to get tangent. That's our first part done. For the second part, since it's not in a trig function, we do actually just have to use the inverse trig function. That's how it goes sometimes. And that gives us our final answer. I hope this demonstration has been useful, and that you decide to make your purchase of trig substitution today.